Hello and welcome back. Today we are going to be talking about a new lesson in our Unit 9 circles. Today is going to be find arc measures and use inscribed angles and polygons. So, of course, I'm Mr. Keeney and I'll be learning you today. So let's go ahead and start right with our vocab. So the first term we're going to talk about today is central angle. And a central angle is an angle whose vertex is the center point of a circle. So I'm going to give these points some names real quick. So we have a angle here, ABC, as you can see, and this angle right here is a central angle because point C, which is right here, is in the center of the circle. And we would simply write this angle just like we would every angle, angle ACB. I chose C to be in the center because C is the vertex of the angle, and that vertex has to be the center point for it to be a center angle. All right, moving on. Our next vocab word we're going to talk about, actually we're going to do 2 and 1, and let me go ahead and get some points here. So we'll call this one, we'll say A, we'll call this one C, we'll call this one B, I guess, and I'm actually going to add a new point. I'm going to add it over here, and there it goes, right there. And I'm going to call this one, we'll go M. So for this slide, I want to talk about minor arcs. And I want to talk about major arcs. And the difference between the two. So a minor arc is a central angle, or I'm sorry, it's an arc that has less than 180 degrees. So an example of a minor arc would actually be arc AB right here, because this is going to be less than 180 degrees. Remember, 180 degrees is a straight line. And so how we note that, or our notation for minor arcs, are we're going to use AB to name it, because those are the 2 points that connect the arc, and we put a little arc symbol over it. So for minor arcs, we have less than 180 degrees, and we use 2 letters for the notation. Now, if we are looking at major arcs are actually a little bit different. Let me see if I can get a different color here. I don't know if I'll be able to. That should be good. So major arcs are greater than 180 degrees, so that's going to be this arc here. As you can see, it is going to go around the circle. It is greater than 180 degrees. And to name, and here's the big difference with notation. For major arcs, we actually need 3 points, which is why I added point M there. So I need to call this one AMB. Notice that AMB, I use A and B to be the first and last letter because those are kind of my endpoints per se for the arc. So major arcs bigger than 180 degrees, minor arcs less than 180 degrees. Major arcs we need 3 letters, minor arcs 2 letters. And this 3 letters, 2 letters kind of helps us. Okay, which arc are we talking about? If we just call major arcs with 2 letters, and then if I say arc AB, I don't know if I'm talking about the AB the minor arc or AB the major arc. So to help us with that, we have our notation differences. And so we have minor arcs, again, one more time. Minor arcs are less than 180 degrees, and major arcs are greater than 180. And I totally messed that up, but we're going to move on anyway. And the last thing here for arcs is this is a semicircle slide, semicircle. And a semicircle is an arc that is exactly, so it's equal to 180 degrees. And so for this one, we use 3 letters as well. So let me go ahead and add a point out here, and we'll stick with A, we'll call this one B and C. And so I would call this one A, B, C. And the reason why we use 3 letters is, what if I have over here I have M. So another semicircle for this example would be AMC. So it just kind of helps us distinguish which way we're going. ABC would be this way, and then let's see if I can get back to that color probably won't be able to be honest. AMC, not too bad. AMC this way would be the other semicircle. So, kind of getting us set up with vocab. Let's see what we got next. Congruent arcs. So, if we have central angles that are congruent, so in this picture, these central angles, they're vertical angles, so they are congruent. And let's go ahead and give these points some name too. AB, CD. So we already know that these angles are congruent, but now what we can say is since their central angles are congruent, we actually can say that arc AB is congruent to arc CD. I think my phone just went off, so if you heard that, Mr. Keeney's super popular. So, let's see here. The first and kind of the only property that we're going to deal with arcs real quick is the measure of a minor arc is the measure of its central angle. And we've kind of talked about this before, but if we add this picture, that's a big dot, but we're going to make do with it. If we have a central angle and we have x degrees, that means its arc is going to be that same number of x degrees. So, and to further illustrate that, we'll bring in a circle, maybe. So if we said that this was, I don't know, 60 degrees, then this arc up here would have to be 60 degrees as well. So, let's go ahead and move on to an example. So MQ and NR diameters of circle O determine whether the given arc is a minor arc, major arc, or semicircle. Then find the measure of the arc. So looking at MN, and MN I can find over here in my picture. MN is actually going to be, and I can tell it's going to be a minor arc. And it's right here. There's M, there's N, so it's this arc created by those two. And it's actually, its central angle, we don't know the measure, but its vertical angle is 73. So this is going to be 73 degrees. So MN is also going to be 73 degrees. All right, and maybe I'll change colors so we know which one I'm on. MP, so now I'm looking at M to P. So I'm going from M all the way around to P. So M to P, I would have to add 73 and 81. Let me go ahead and back up here. So for M to P, I have to do 73 plus 81, so that's going to be 154 degrees, and that is less than 180, so again, this is a minor arc. So again, minor arcs are less than 180, major are bigger than 180, semicircles exactly. Let's see here. PN, so PN looks like, and I'll change colors. PN, P to N, this arc, and I can see real quick that that is going to be 81 degrees because its central angle right here is 81 degrees, and that again is a minor arc because it's less than 180. Now MRQ, and this right here kind of gives it away. I can say right now that it is going to be a major or a semicircle. Mr. Keeney can't spell, he's a math teacher. Major or semicircle. And the reason why I know that is that there's 3 letters. So really I'm just deciding between major or semicircle. So actually I'm going to erase all that because I need to make sure which one it's going to be. So let's go ahead and look at MRQ. So I'm going from M to R to Q. And so no, that's going to be, looks like it's going to be 73 plus whatever this angle is over here. So I'm going to go and back up with those signs here. Oop, that's going to be minor. Well, I can see that this is 73, this is 81, and it looks like they told me that NR is a diameter, so 81 plus 73, we already did that as 154. So the reason why that's important is if I do 180 minus 154, this here in the middle has to be 26 because 81 plus 26 plus 73 equals 180. 81 plus 26 is 107, and that would be a central angle This is going to be congruent to this. So this is over here 107 degrees. So really what I'm doing is 107 plus 73, which is 180 degrees. So this will be a semicircle. And now that I have this circle over here, everything is all kind of finished out. It should get a lot quicker for the second column. For example, in Q, I'm looking at from N to Q, so that would be 81 plus 26. 81 plus 26, which is 107. Another way I could have done that is look at its vertical angle here. And let me switch colors again one more time. But this is going to be 107, and that is less than 180, so that is minor. MRP, M to R to P, going all the way around, so I'm doing 107 plus 73 plus 26. So when I add those up, I get 206. So this is 206 degrees. That is bigger than 180, so this is a major arc. MNQ, 73 plus 81 plus 26. And I'm doing my calculator work over here actually, and that actually equals 180. So if I'm looking at MNQ, and actually I should have known that because MQ is the diameter, so it's going to cut it in half. So that's going to be 180 degrees, and that is a semicircle. And MRN is our last one, MRN, so I'm going M to R all the way around to N. So I'm just going to do 360 as a whole circle minus this 73 degrees here that is not included, and that should give me the arc degrees. So 360 minus 73 is 287 degrees, and that would be a major arc. So that is a look at our first kind of examples. Let's move on to, oh, and I got some blank pages here. Let's move on to kind of our next vocab. What this is showing me right now is an inscribed angle. And an inscribed angle is an angle whose vertex is on the circle. So we talked about a central angle, but this is an inscribed angle because that vertex that I just showed right there, that is on the circle. So central angle, vertex in the center, inscribed angle, vertex who is on the circle, and whose sides are chords of the circle. As you can see, they can still extend on. They can extend on these rays, but the sides of the angle, those segments, create chords. So this is an inscribed angle. And we're going to have some examples and some ways that we can use this and some properties that's going to go along with it. Now, to go along with inscribed angle, we actually have an intercepted arc, which is, looking at this picture, is this right here. So let me draw an arrow. This is the inscribed angle, the actual angle, and this red part is the intercepted arc. Intercepted arc. And so we have this relationship here of inscribed angle. The sides come out, those chords or those rays come out and form the intercepted arc of that circle. So inscribed angle to its intercepted arc, and we're going to learn a property about that soon. But I want to go on to this next slide. This right here, well, both of these are examples of inscribed polygon. And inscribed polygons are a polygon that has all its vertices on a circle. So if I'm looking at these examples, I got the vertices of this triangle all on the circle, and for this quadrilateral, its vertices are all on the circle. So these are examples of inscribed polygons. This one up here being a inscribed triangle. And as you can guess, and maybe I'll abbreviate this, well, no, might as well go all the way out. Inscribed quadrilateral. And so we're going to learn a couple things about those as well. And here is kind of that property page. So, and actually before we go back, I do want to mention something, that these circles here, so both this circle and this circle, those circles have a name. Those are called circumscribed circles. But moving on. So the first thing here, the measures of an inscribed angle. So to show you a picture, an inscribed angle, we've got this kind of situation going on. An inscribed angle is half the measure of its intercepted arc. So that means that whatever this inscribed angle's measure is, x degrees, this intercepted arc is double it, or as this property is saying is, the inscribed angle is half of 2x is x, is half the measure of that intercepted arc. So going from angle to arc, we're just doubling it, and going from arc to angle, we're just taking half of it. So that makes it kind of a quick relationship. Next property, if two inscribed angles of a circle intercept the same arc, so if they intercept the same arcs, then the angles are congruent. And so this picture is kind of interesting. We have one inscribed angle that goes to arc, and we'll call this arc over here, let's call it arc AB. And so we also have another inscribed angle that has an intercepted arc of AB. So what we can say is that these two angles right here are congruent because they both lead to its intercepted arc AB. So when they have the same intercepted arc, which is said right here, when they have the same intercepted arc, or they intercept the same arc, then the angles are congruent. So to give that a little bit more legs, or some hard kind of line here, angle D is congruent to angle C in this picture because they both have an intersect arc of AB. Next property, a right. So we're coming back to right triangles. It's amazing how much we can use them in circles. A right triangle is inscribed in a circle if and only if the hypotenuse is a diameter of the circle. So kind of what would go here is, let's go ahead, and that looks about through the middle. There's the center of the circle, and let's go ahead and finish up the rest of the triangle. So a right triangle can be inscribed in a circle if and only if the hypotenuse is the diameter. So if we want to have a right triangle, the hypotenuse has to be a diameter of the circle. Otherwise, we're not going to have a right triangle. And the reason that is because if this is 90 degrees, then when I look at its intercepted arc here, well, we learned up here in the first property that if we have x degrees, which is 90 degrees down here, then we just double it, x to 2x. Well, double of 90 is 180. So it should make sense that it has to be the diameter. Diameter cuts it in half. A full circle is 360 degrees, so 180 would be half of it. That's what a diameter does, cuts it in half. And so if we go from 180 to its inscribed angle, 90 degrees, you can see why we have the relationship of the hypotenuse has to be the diameter. So kind of interesting there, but it all kind of works out. So half the circle is 180, take half of that intercepted arc to get the inscribed angle, which has to be 90 degrees. And our last property here is a quadrilateral. Let me switch back to black. A quadrilateral, and I might just say quad, can be inscribed in a circle if and only if its opposite angles are supplementary. So a quad can be inscribed in a circle if and only if its opposite angles are supplementary. So let's go ahead and draw a quadrilateral quick, and we'll give it some points. So there's our quad. We'll say A, we'll say B, C, and D. And what this is saying is that the opposite angles are supplementary. Pretty simple enough. Angle B plus angle C, or I should say, let me back that up. Let me use proper notation if this is going to be on YouTube for people to judge. Measure of angle B plus the measure of angle C equals 180 degrees. And the measure of angle A plus the measure of angle D equals 180 degrees. And that's all it's really saying. If we're going to have a quadrilateral that's inscribed in a circle, then those opposite angles are supplementary. And it goes the other way. If there's a quadrilateral and its opposite angles are supplementary, yes, it can be inscribed in a circle. So now we're going to use all of these properties, and we're going to look at some example problems. Find the indicated measure. And right here for this first one it says find the measure of angle A. Angle A is down here. So if I'm trying to find that, they did give me its intercepted arc. Its intercepted arc is 158. So to get from the intercepted arc down to the inscribed angle, I just take 158 and I divide it by 2. And so if I were to do 158 divided by 2, that would give me 79 degrees. So the measure of angle A is 79 degrees. Using that property, I think that was, if we go back, that was that top one here that we're using. Measure of angle B. Now this one they didn't give me on this first problem. They told me that 158 was the intercepted arc. If I'm looking at the intercepted arc now, which is this right here, they didn't tell me, but what they do show me is that AC right here is a diameter. It goes through the center of the circle. Diameter cuts a circle in half. So this has to be, and that was an awful 8, 180 degrees. And if we go back and we remember, if this is diameter, we know that it has to be a hypotenuse of this triangle. This has to be a right angle. Or we can just take 180 divided by 2. We've already had this conversation before, and we get 90 degrees. So either way, however you're looking at it, if you use the property of the diameter, it has to be the hypotenuse, or 180 divided by 2, you'll get that the measure of angle B is 90 degrees. And this time we're actually finding arc BC, the measure of arc BC. The inscribed angle is 40. So this time I'm taking 40 and I'm multiplying it by 2. And that's easy enough. This would have to be 80 degrees. So the measure of arc BC is 80 degrees. So using a couple of those properties, a lot more we can do with this, a lot more on your homework, but a couple ones to kind of get you familiar with. Multiple choice in the diagram. Angle ADC is a central angle, okay. And measure of ADC is 60 degrees. What is the measure of ABC? Okay, that picture is way too small. Let me draw something real quick. Let's get this a little bit bigger. We got a circle. We'll put the central angle right about there. That looks good enough for the situation. We'll say that. And looks like we've got another point B. So I'm just redrawing the circle right now so you can see my work a little bit better. All right, that might help us work out, and let's get some points A, C, D, and B. All right, let's label some things. ADC is a central angle. Okay, ADC is central angle, and ADC is, oh, that's the same angle, is 60 degrees, so this is 60 degrees. Cool. Well, actually, before I even get to what I'm looking at, if that's a central angle that's 60 degrees, then I know that the intercepted arc is 60 degrees. So I know that because this is 60 degrees, the central angle and the actually not intercepted arc, just the central angle and its arc is they're congruent, so that's 60 degrees. Okay, what is the measure of ABC? ABC, so we're looking at ABC. Okay, so this is an inscribed angle. So inscribed angle, we would take going from, let me change colors. going from 60 degrees back down to the inscribed angle, I would have to take half of it. So I'm looking at 60 and I'm taking half of that. So that would be 30 degrees. So the measure of angle ABC would be half of 60 degrees, so that's 30 degrees. And I look here, and that's choice B. So pretty simple enough. We use the relationship of a central angle. Central angle and its arc, like I showed right here, and I'll show it again, is they're just congruents. 60 degrees, 60 degrees. But going from, and this is a intercepted arc to an inscribed angle, I have to take half of it like I did right here. So I think that brings us to the end. So that was kind of a wild ride. That was a lot of information, but hopefully that helps you out if you're at home trying to figure all this out or just need some help or you just want to see what I'm doing. So this has been Mr. Keeney. Hopefully I learned you a little bit today. Hopefully you learned in class and you didn't have to watch this. But if you did and you just enjoy math, then I hope you enjoyed. I hope you learned something. And if you have any questions, again, just let me know. A lot of you guys know how to reach me. If not, leave a comment below and I will get back to you. So thank you for watching, and I'll talk to you guys later.